Okay, I guess there are no questions, then let me proceed. So yeah, now we had found that, so now what happens is the actual curve that is actually observed experimentally is if you start to compress the the pure component. Okay, this is from thermodynamics, of course. So we are going to follow like this. Okay, and then this follows like this, and at certain temperature, or at certain pressure, the pressure is going to remain constant, and then beyond that, then again there will be two phases formed with uh, volume fraction values given respectively by two numbers which are widely separated. That is a characteristic. This is widely separated. So as you are moving from here to here, your molar volume is continuously changing. Okay, it's a continuous variable, and at this point there's a jump. Okay, so it basically exists. All right, so sorry, two states of aggregations, okay, which is widely separated in terms of its molar volumes. That essentially physically it means that the molar volumes are, I mean, the states of aggregation are such that the densities are extremely different. There's a wide difference in the densities of these two states of aggregation, these and this. Okay, and these are identified as liquid and vapor phases. The one with a larger molar volume is vapor phase. One with a smaller molar volume or larger density is the liquid phase. And then after when all the material converts from vapor to liquid, then only the pressure starts to rise. And that rise in pressure is extremely steep as compared to other side. This was like compressible vapor, which can be easily compressed. Okay, but here it has turned into liquid now, and this branch of the curve corresponds to complete liquefaction, right? And here I have two phase region. Okay, so that will depend on what is how much you have compressed. As you compress, the overall molar volume is going to follow this line. Okay, so it's going to follow this line, going to decrease as you compress this vessel. The volume is of course is going to decrease. Okay, but your pressure is going to remain constant. It will decrease. So it will decrease at a constant pressure, and then it will going to increase up, right? So this is the kind of pressure temperature curve shown by green curve is what is observed. That is partially predicted the uh, by our van der Waals equation of state. Now, why did I say partially predicted? Now, question is why should it not go like this? Okay. Well, so first thing we can rule out this part. Basically, this part I have the compressibility value which is unphysical. That will never be observed. So this part will never be observed. And this part, there is a phase equilibrium established. Okay. So now if you remember, so let me move on then. So now I'm going to talk about just the part which was straight line. So let me redraw this curve. Okay. So observed curve looks like this, very sharp increase in pressure with small change in volume. That means very small compressibility, very high incompressibility. Then a flat line, okay, and then a very smooth, very uh, compressible kind of behavior observed over here. This sharp trend is basically liquid phase. This is vapor phase. Okay, and this part is two phase equilibrium. Okay, and I'm sorry, and my this uh, this curve, the van der Waals equation of state curve predicts something which is not shown up here, but shown in red colored table. Okay. So the question is, if I if I am, so this is at, let's say, pressure. This axis is pressure, and this axis is temperature. Okay. Hello, hello, hello. All right. I'm sorry about that. So, okay. Now the question is, where do you draw this horizontal line? Okay. Where, up to what pressure can you compress before it starts to form a two-phase, starts to depict a two-phase behavior? Okay. So where, so when I am compressing it, when I'm compressing it this way, okay. So up to what up to what compression I can keep on going? Okay. Sorry, this is, I'm sorry about this. This is not wrong. This is vapor. Sorry, volume, volumetric pressure, molar volume, and this is at constant temperature. Sorry about that. Okay. So the question is, as I compress at constant temperature, up to what volume, molar volume, or up to what pressure should I compress before it starts to transform to a new state of aggregation? That is a question you can ask. So basically, the question we are asking is two-phase equilibrium. When does two-phase equilibrium establish, right? And well, I'm not going to detail of that. This is thermodynamics problem. The condition for two-phase equilibrium in single component system is temperature should be equal, okay, pressure should be equal, and something else. What's the other thing? Other thing is chemical potential, or G's should be equal, right? So G under bar should be the same in the two phases. And by the way, molar Gibbs free energy happens to be the same as chemical potential in pure systems. Just, I hope you all are familiar with that. G bar and mu are the same in pure components. That will not hold in mixtures. Okay, not so in mixtures. Some mixtures, you talk about partial Gibbs free energy rather than molar Gibbs free energy. Okay. Anyway, so this is what I have to ensure. Okay, in order to have this, I have to ensure that these quantities have to be equal in the two phases, which are identified as these 2 points. Okay, now temperature is already the same because I am running this curve at constant temperature. That's not a problem. So temperature for this point is anyway the same because these 2 points lie on an isotherm. Okay? These 2 points, according to the equation of state, they must lie on isotherm. Therefore, here and here the temperatures are the same. That is already established. Pressure is the same, but we do not know where it is, right? So because of the horizontality of this line, the pressure of these 2 points are to be the same. But we do not know, I mean, where do we go like this, or do we go like this, or do we go like this? How do we, where do we go like this, or do we go like this? I mean, where does this horizontal line appear is not known to us at the moment. So how do we find that out? Well, so that is so basically temperature is the same, okay, because, well, I should not say it is the same. I should say equality in temperature is ensured. Equality of the temperature is ensured because the two phases belong to an isotherm. Okay. Second is equality of pressure is ensured because ensured by basically this idea that this line is horizontal, okay, by the uh, by the by the design or by the fact that um, the two phases, two phases, two phases, okay, lie on the horizontal line. Okay, so that ensures this lies, but we still do not know where does that horizontal line appear. Okay, the question is where to place this horizontal line, at what pressure. That question is basically answered by the third equality. So from equality of G under bar. And what do you do here? So basically, if you write this down, G under bar in phase liquid is the same as G under bar in the phase vapor. Okay. So if you remember, that would mean that G under bar liquid minus G under bar vapor is 0. Okay. This is done at, so that would mean, if you remember, G dg, basically dg under bar is vdp minus, I think it was s dt, suppose. So s dt. Okay. All right. So this would be according to the equation of state. Okay. According to the equation of state. Okay. So now equation of state is basically isothermal equation of state. So this term dt is 0. Okay. So if I go from this state, let's say call this state as 1, and let's call this state as 2. Okay. So there's a liquid and vapor states basically. So that tells me that delta G bar from liquid to vapor or from vapor to liquid, okay, that is 0. So that would mean that dg integral from liquid to vapor or vice versa, this should be equal to 0. That should be equal to integral vdp from liquid vapor state to vapor state minus s bar dt from liquid to vapor state, right? And this has to be done. So now I'm constructing it to be done on isothermally from liquid to vapor state. That means I'm going to go from this one to this one following this curve. Okay, right? The isothermal equation of state. So if that is the case, then this will go to 0, and I'll get the equation which is v bar dp integral is 0 along this curve. So if you just look at this equation, this condition by which we obtained where to place the horizontal constant pressure line is obtained uh, by enforcing this condition, which is V bar dP from liquid to vapor or vapor to liquid along the state of equation state. Okay, so this would be, this integration is done along the isotherm. See, that should be equal to 0. So now if you look at this, if you geometrically, what it means is the following. Okay, geometrically it means that going from here to here and here to here, if the net integral is 0, now this is pressure, this is volume, right? So this, if you just flip it, okay, this will be y dx integral, and this part will be positive, this part will be negative. If you flip this, okay, because if you flip this, right, in terms of y dx form, So that P becomes horizontal axis, uh, V bar becomes a vertical axis, then it's going to look like this, right? And I have to find this point, right? So I have to go from here to here. Now, if you go this way, so area under this part and this curve, VDP integral will be essentially this area minus this area. Okay? This is area 1, and this is area 2. So that tells me that area 1 minus area 2 should be equal to 0. Okay, and that gives me the condition of where to place this horizontal line. I have several possibilities, but only one possibility will be chosen so that this area will become equal to this area. Okay? So area 1 equals to area 2. All right. So now, this is the so now having done this, we have basically found out under a given for a given temperature, if I fix a temperature, that means if I fix a isotherm, I know what will be at what pressure, what will the equilibrium vapor pressure, okay, that will be the vapor pressure of the material of the liquid, and what will be the molar volumes of the two phases. Okay, but that information can be obtained by doing this. So now here, what we need actually, so we already know the V bar dependence on P from the equation of state. Okay, at a given temperature, I can find out V bar dependence on P and then integrate it. So that may form a simple project for you guys to, for example, choose a liquid, okay? And I want probably maybe two of you to team up and find your favorite liquid and do this calculation, your phase behavior that you predict from assuming that it's a Van der Waals liquid. Okay? So all you need to do now is basically you need to know. Okay, so what is it that I want to know is how to compute it. So computing the integral. Okay, so this you can check yourself. Okay, we will talk about how to. So a lot of times this kind of integrals are easy to be obtained analytically. But as I told you, like many equations you cannot solve analytically, many algebraic equations you cannot solve analytically, many differential equations you cannot solve analytically, and similarly many integrals you may not be able to evaluate analytically. In such cases, you have to resort to computing techniques, computers, and there are methods to compute integrals. I'm sure you have been exposed to that. You can use, for example, excuse me, you can use, I think, trapezoidal rule, or there are many kind of methods. There are 3-point, 5-point methods, right? So I hope you are familiar with those. So all you need to do, Simpson's rule, right? 3-point Simpson, 5-point Simpson's rule, right? So if you're already familiar, that's great. So all you need to do is you have to basically start with a guessed value, okay? And then starting with a guessed value pressure, so suppose I fixed a pressure, let's say P0 or some P0, okay? That and then you have to find out at this P0 where will this curve, what will be the, if you fix the P0, you'll get a nonlinear algebraic equation for which you have to solve, you get three roots, okay? You have to find these values, okay? One will be the smallest one will be the largest one. Then you do the integral from the smallest to the intermediate point and intermediate to the next one, and then compare, okay? So when you do this, you go from here to here and then here to here. Okay, compare. If it matches, great, you've found the answer in one step. If this one is larger, you reduce the value, okay, and keep on going until you meet your desired result, which is these two areas become equal after these integrals. Okay, so basically you have to ensure that V bar dp from, let's say, point, this is point A, this is point B, this is point C. So A to B is the same as V bar dp B to C. Okay, integration has to be done with a particular functional form of V bar on E. Okay, at a given t, of course, so at a given isotherm, at given t, I know v bar as a function of t. Okay, I can evaluate this integral either numerically, whichever is convenient for you. Do that and find out. I want you guys to do this exercise yourself. Okay, and then you will find out for different, and then you repeat the same thing. Once you have found it, you record these values. Okay, record pa, pb, pc for that t, and then keep on changing t and doing this, iterate it for basically repeat it for all the different values of t, starting from a very low value of t to very high value of t, and then obtain basically a curve, binodal point curve and spinodal curves. Okay, which is these point to track the minima and max. Forget the spinodal at the moment, but you should at least get me the. You should also at least be able to calculate the binodal curve and the critical point, and then you can compare that critical point to what you expect from analytical results for van der Waals equation of state and what is the actual value. And then I want you to do the same procedure for Peng-Robinson equation of state. Okay, so do this using two things, using van der Waals equation of state. Okay, van der Waals equation of state will check your method is correct or not, because your analytical results are available here. Okay, in terms of critical points, etc., analytical results are available. Okay, because you can calculate TC in terms of AB parameters. Okay, so you can always find out TC from this procedure. You find a TC in this from this procedure, and then you can, if you already know A and B, of course, if you're using van der Waals, you will be knowing A and B. Then compare your computed TC with the what you predict the TC to be from A and B parameters for the van der Waals gas. You all probably know that how to find TC in terms of A and B. Okay, if you have van der Waals equation state. Or and secondly, you make it a little more complicated and apply Peng-Robinson equation of state when you evaluate these two integrals. Okay, and do the same procedure. So all you need to do is just change this functional form. Okay, in the second step. The rest of the method is, the algorithm is still the same. Just change this and change this functional form, and then compute your critical point for a pure liquid of your choice. Okay. All right. So I hope this is clear to everyone. Please do that. Okay. All right. Now, next, I would want to talk about, and by the way, just for the sake of completeness, let me write down the Peng-Robinson equation state. That is given that T equals to RT over V bar minus B minus Q over V bar plus P plus P V bar minus B. Okay. And actually, maybe I can just write it down here. In general, so these are the examples of cubic equations state. Okay, where if you define compressibility factor, if you all are familiar with that, is alpha multiplied here. Alpha, where is alpha? Okay, eccentric factor. Okay, so that well, I am assuming that we can ignore alpha is 1 at the moment. Let's say your eccentric factor is 1 in spherical shape, right? So we can assume that eccentric factor is 1. Okay, so to define compressibility factor PV bar over RT, we call it Z. Then all these different equations state can be written in a simple form which is ZQ plus alpha Z square plus beta C plus gamma, which goes to okay, in terms of Z. And if you compare van der Waals and Penn Robinson equation of states, then alpha, beta, and gamma values are given by -1, -b. I'm just copying it down from where. Okay, so it's nothing that you need to remember, but you need to know how to use it at least. Okay, and minus plus square plus q, where B is capital B is P over T, and capital Q is P over T square. Okay. So knowing A and B parameters, okay, you should be able to obtain this cubic equation of state in terms of Z. Okay, Z is the compressibility factor. All right, so this is just a bunch of facts that you have to be aware of. That's all. Nothing more conceptually important here. Well, conceptual importance here is that you can write it in a simplified form. That's the important thing. Okay. All right. And this you can do for even other equations, straight like Redlich form or LKS, etc. Okay. All right. Now, one more example I want to take up is about where you need to use, for example, where you need to use, for example, one of the methods that we have talked, that is the nonlinear algebraic equations. Okay, so that again, this example is again from thermodynamics. So VLE calculations. So you all probably remember mixtures. Now we are talking about mixtures, and here let's constrain ourselves binary mixtures. Let's talk about only binary mixtures. Okay. So what we want here is VL. You all probably are familiar with that. VL information can be expressed multiple ways. One of the ways is you write down, let's say you fix constant temperature, okay, and you plot bubble point pressure and dew point pressures as you change the composition. Okay, so that is what you obtain. So this experiment is done in a vessel where you where you fix the temperature and you just change the composition of the liquid and so for different composition you perform the experiment of compression or decompression and see when your mixture complete. So when you start to at very low pressure it will be vapor, okay, and very high pressure it will be liquid, okay, and in between there will be 2 points, okay, where the first there will be dew point, okay, and there will be a bubble point. Here if you start from very high pressure and start to decompress, where the first bubble will appear, that is the bubble point pressure, and you all probably know that, okay, and do that for all different composition, you will get a curve that might look like this, okay. These points are pure component vapor pressures at this temperature, right? So this is P1 and this is P2 vapor pressure, where X is basically X2, that is increasing this side this way, so that this is pure 2 and this is pure, this end is pure 1. Okay, this all we all know. That is one way of representing the VLE behavior, vapor liquid equilibrium behavior. You can do the same thing at constant pressure, okay, and you can just you can rather than when measuring dew points and bubble points at constant pressure, you measure it at different at constant dew point temperatures, and rather than measuring dew point pressures and bubble point pressures, you measure dew point temperatures and bubble point temperatures at constant pressure. And again, this is pure 2, this is pure 1, and it might look like this, okay. So here I have the low temperature phase is liquid, high temperature phase is liquid. Okay. Okay. So and these are one phase regions, and this is my two phase region. Okay, and in the here these are the basically at this pressure your liquid and vapor will be formed having these compositions. The top curve is identified. If you vary on top, if you're looking at this curve, you basically your composition variable is termed as x. Okay, if you're changing on this curve, your composition variable is termed as y, but they are actually the same thing. They are both composition variables. And similarly here, this composition variable is x, and on this curve, the composition variable is y. Okay. All right. So that is these are two methods. Other alternatively, you can also get rid of these. You can actually eliminate temperature or pressure from your calculation. For example, over here, I can forget about temperature at all completely, and I'll just look at the set of these 2 points, okay, which are I'll just look at there's a unique dependence on x and y. Okay, there's a unique dependence on x and y. So that way you actually eliminate temperature. So for each x there's a unique y. Okay, at what temperature that occurs, we are not concerned with that. We are only concerned with the fact that if I am given the x, that means the liquid composition, what is the vapor composition? That is y. Okay, so that is obtained by simply doing, for example, you can call this, and you can imagine a y equals to x line, y going from 0 to 1, x going from 0 to 1. Okay, and all we need to do is, for example, I can take this is my x curve. So that would this point, for example, it's I'm at this point, I'll directly take it over here. So this would belong to this point. Okay, and this point would belong to this point. The corresponding y point would belong to, just take this and then reflect it off this diagonal line. Okay, wherever it meets, that would be my point representing the equilibrium line, which is shown here. Okay? So this equilibrium line is shown by this point, this curve. Okay? So you do that same thing for each. Okay? So for example, here I take this, and then we take this point and then reflect it off with this. Okay? So this way you're going to get a curve that will look like this. Okay, so this would be y versus x curve. Okay, all right, and y versus x curve is actually nothing but representing the same information, but it hides the temperature dependencies. It just does not tell me that this x and y will appear at what temperature, or this any line, any point falling on this curve will appear at what temperature. Okay, so that way it hides the temperature information. Okay, all right, so these are the different ways of finding out, just revising this quickly. So these are different ways of finding out VLE curve. Michael, now what I want you to do is actually compute the VLE curves. Okay, so know how to compute VLE curves. I'll just look up one example problem. So VLE curve calculations for, let's say, ethyl acetate and benzene mixture. Okay, and the reason I'm taking up this up because it involves use of solving nonlinear algebraic equation system. Okay, that is involved here. So now some information that is given here. So some data is provided. First of all, it's known that it forms an azeotrope. This mixture forms an azeotrope at X ethyl acetate composition of a liquid composition. If you take ethyl acetate to this one, so that rather benzene is 0.41. So this composition at temperature of 75 degrees centigrade and pressure of 1.17 bar. Okay, that is one information available. That is something that was experimentally found, and one can that's easy to establish. Okay, so the idea is basically obtain as much information as possible with the least number of experiments or least set of experimental effort, least amount of experimental effort, right? So this is one experimental data available. Other experimental data pertain to the pure components separately. That is this. The vapor pressures of the pure ethyl acetate and benzene are known as from temperature dependence. Let me just write this down. So this is given to us, and this is an equation that can be obtained from thermodynamics. The form can be obtained from thermodynamics. Okay, I hope you all have studied that. This is generalized equation. Minus 10.5 divided by T minus 51.256. Okay. So we need to basically find out based on this. If I now take a mixture or any composition for liquid and for liquid ethyl acetate and benzene, what would be the composition which is in equilibrium with its vapor phase, right? So let's call. By the way, these two expressions, I know pressure is in bar, temperature is in kelvins. Okay. Okay. Now let's call ethyl acetate as component. Let's label them. Enumerate them as 1 and 2. Okay. Now, how do we proceed? First thing, again, I don't want to review the entire thermodynamics, but I'll just quickly tell you the equilibrium condition is that the partial fugacities of each component in each phase or chemical potentials of each component in each phase should be equal, right? Of course, temperature and pressure are also equal, right? So and temperature and pressure. Okay, so we'll consider. Let's say you want to find out constant pressure XY curve. Okay, so say XY curve at a constant pressure. Okay. So basically, remember this. So remember this curve. So this constant pressure curve will give you one kind of x and y. Constant temperature curve will give you another kind of x and y. Okay, so that has to be kept in mind. Okay. All right. So x and y curve can be basically associated at a constant, can be obtained at a constant temperature or constant pressure for a binary system. All right. Okay. Now. So okay, so so what does this relation give us? Now again, in liquid phase, we'll assume since it is forming, it's known to form a an azeotrope, right? That would imply it's a non-ideal mixture in liquid. Okay, that can only happen only when there is non-ideality. And I hope you all are familiar with this idea of non-ideality. I will not go into that. Okay, so if there is a non-ideality, the activity coefficient is not equal to 1. Okay, it only non-ideality only is a factor that compares interaction between pairs, okay, as compared to their pure state, molecular interactions. If the molecular interactions as compared to the mixtures in pure state, if it changes as you mix them, then there is a non-ideality, which so interactions change upon mixing. That is non-ideal mixing. Okay, so non-ideal mixtures, there is a altered interaction as compared to their pure states, pure conditions. All right. Okay, so there is a very simple form of that. First of all, we can so approximation involved here is that we'll assume that vapor phase is ideal. Okay, so that right hand side is given by simply composition times operational pressure, total pressure, actual pressure. Okay, and left hand side is given by xi, gamma I, and I vapor pressure. Okay, so this is our working equation. I hope you are, at least chemical engineering students should be familiar with this expression, this equation. What kind of assumptions we have made here? Assumptions you have to be uh, careful, or you have to be aware of. First of all, of course, the vapor phase is ideal. Okay, and this side, the fugacity of liquid of any component in liquid phase, basically fugacity of, so when you have pure liquid, okay, there will be, so we assume that vapor pressure of the pure liquid is also low enough. Okay, so that you can, for pure liquid, the fugacity uh, can be approximated by the vapor pressure. Okay. So this is for pure case. This equation is for pure liquid I, pure component I. Okay. So pure component I, my fugacity is approximated by the vapor pressure, and that's why I have this vapor pressure appearing here. And then you're diluting it in the mixture, so that dilution will lead to a factor multiplication of factor xi, and then you're incorporating non-ideality, that will be gamma. Okay, that's it. So so there are steps. First, you dilute, that changes the fugacity, and then you make it non-ideal, that further changes the fugacity. And those two effects are accounted for by these factors of and gamma I, that is activity coefficient. Okay. All right. So with this, if I just write this down, I have F1 liquid equals to F1 vapor, F2 liquid equal to F2 vapor, that is partial. Okay, this would imply, basically in general, uh, this would imply, well, I have already written it, gamma I xi Pi vapor pressure equals to E times Yi. I can be 1 or 2. This is components. Component. Okay, and liquid and vapor phase notations, right? Okay, so what does that give us? That gives us, let's say, Py1 equals to gamma 1 x1 P1 vapor pressure, okay, and gamma 1 x1. This, of course, has a form of that, right? So, for example, here I'll have x0 minus 2842.2 divided by t minus 56.3209, and py2 will be equal to gamma 2 x2 into 9.3171 minus 2810.5 divided by t minus 51.2586. Okay. All right, now you have to remember that gamma 1 and gamma 2 are functions of temperature, pressure, etc. and composition. Okay, so let's say the function of composition, okay, just call it, is a function of composition at given temperature and pressure. Okay, so how do you find that out? So we can use, there are several models, liquid activity coefficient models, and I'm sure you must have studied that. One of them is Van Laar's model for non-ideal mixtures. Okay, so Van Laar's model, and once we use that, if you don't know, don't worry. I'll just give you the equations of the model are as follows. I'll just give you the equations of the model. This model predicts the activity coefficient of a binary mixture with a given composition. Okay, so x1 and x2 we know. Of course, x2 will, okay, so we'll come to that later. And then ln gamma 2 would be equal to beta over 1 plus beta over alpha x2 by x1 whole square. Okay, this is Van Laar's model. Okay, so that is one of the very celebrated liquid activity coefficient model, and a good starting point for non-ideal binary mixtures. It's a good starting point. There are more detailed models, but we need more and more parameters if you go to more detailed models. Here I have only two parameters, one alpha and beta. Okay, so these are the two unknowns. Given these two unknowns, I can find out gamma 1 at any composition of the liquid. Okay, and gamma 2 at any for any composition as well. Okay, so it's a good starting point for non-ideal binary mixture. Okay, now how do we find alpha and beta? So, well, remember we have not yet utilized the you already utilized these two equations in our method procedure, but we have not yet utilized this piece of information. Okay, so if you utilize that information, okay, let's see. So what we know at azeotrope point, at an azeotropic point, what do I know? I know x1 equal to y1 and x2 equal to y2, of course. Okay. Now, if I apply VLE condition at azeotropic, okay, VLE condition, if you apply, that will give me gamma 1 x1 P1 vapor pressure equals to 1 P, and gamma 2 x2 P2 vapor pressure equals to y2 P. Okay. Now I know that x1 equal to y1, so this cancels out, this cancels. Okay, and we already know. Okay, so that will give me gamma 1 equals to P over P1 vapor pressure, and this will give me gamma 2 equals to P over P2 vapor pressure. Now I know that azeotropic composition temperature was T is given to be 75 degrees centigrade, pressure was 1.17 bar. Okay, so knowing temperature, okay, I can find out P1 vapor pressure and P2 vapor pressure from these Antoine equations, right? So vapor pressures can be obtained. Okay, and total pressure, if you so at azeotropic composition, this pressure is known also, which is 1.17 bar. Okay, so these numerators are known, denominators are known. Gamma 1 and gamma 2 values are known. Now x1 and x2 are also known. Okay, so azeotropic point x1 was found given to be 0.581. Okay, and therefore x2 will be equal to 0.419. Okay, so x1 and x2 are given. Okay, so therefore gamma 1 has been obtained from these two numbers. Okay, so I can find out left hand side in these two equations. Okay, in one Van Laar's model, x1 and x2 are known. Okay, so this becomes essentially two equations in two unknowns. which are alpha and beta. Okay, and these equations are nonlinear. Okay, so you solve for alpha and beta over here. Okay, so this basically gives. Okay, so this gives equations, or I should say nonlinear equations, nonlinear algebraic equations in alpha and beta to solve it using, you can use the graphs. Okay, so now having done that, okay, you have found alpha and beta. So now you know generally how gamma 1. So what you did here is you utilize a single point data, which is azeotropic point data, to predict how gamma 1 will vary with composition. Okay, so that is what we basically achieved by doing this procedure. Right now I know how gamma 1 depends on how gamma 1 dip. Okay, so I think just a couple of more minutes and we'll be through. So now I know how gamma 1 depends on compositions. Alpha and beta are known to me. I can now substitute it over here. Okay, that is these expressions. Okay, and I'll have the necessary equations which would give me the VLE curves, right? So that would be, if I just write it in detail, so if I write it in detail, that would look like uh, y1 equals to exponential alpha over 1 plus alpha by beta x1 by x2 square. That is my gamma 1, okay, into x1 into 9.6830 minus 2842.2 divided by t minus 56.8209. Okay, ey2 would be equal to exponential beta over 1 plus beta over alpha x2 over x1 whole square. Okay, so this is your gamma 2, okay, into x2 into 9.3171 minus 2810.5 divided by t minus 51.2586. Okay, all right, so these are my two equations. What are my unknowns? X1, X2, Y1, and Y2. Okay, I need two more equations which are actually given by these two conditions on Y1 and X1, Y2 and X2. Sorry, two. Okay, so we have four equations, four unknowns. These are nonlinear algebraic equations. Solve them and find out your answers at given temperature, right? So change the temperature. Okay, remember fixed pressure. Okay, change temperature. Solve for x1, x2, y1, and y2. Okay, and then plot. Okay, y1 versus x1 or y2 versus x2. That you should be able to do yourself. All right, so I'm going to leave it here and then expect you to perform these calculations on your own. Okay, because you already know uh, Newton Raphson method. Now some of you are in trouble with implementing it on MATLAB. uh, okay, and so tomorrow onwards I'll probably spend some time on talking about MATLAB so that you're all set for further calculations for doing your own on your own. Okay. So all right. Well, stop the class unless there is a question. Any question? Okay. Let's see the questions so far. Okay. All right, then I'll stop here and we'll start tomorrow.